Hey, it's Ross from rosslukeman.com. Today I have a really fun experiment in measuring voltage drop. So voltage drop in a system is kind of a silent thief where you send out a certain voltage from a charger like this and it doesn't all make it to the battery, and that power in between is wasted as those electrons race. You can think of it kind of like a race course with obstacles, right? The electrons race out on the positive, and they're going to run through the bus bar, through this switch, through the fuse, through the battery, and they're going to return through this shunt and back to the charger. So it's quite a lot of obstacles that the electrons have to go through, and they are slamming into things as they run through these cables and these various elements. And I was playing around charging my battery the other night. I have to charge this battery in between these demonstrations. And I got my multimeter and I started measuring the different voltages. Rule number one with measuring voltage drop is you have to have some current flowing through that line, because as it stands now, everything is off and the voltage here is going to be the same as the voltage at the battery. Everything looks great. Well, once we get that current flowing through those lines, then we start to see the result of the resistance in these lines. So I want to do some fun experiments with switching out these lines. You can see they're kind of sloppy as I have them. These could be shorter. These are 6-gauge cables that are specified for this 30 amp charger from Victron. And what we're going to do is we are going to put some ridiculously small cables. Now, I have to say, don't try this at home. The cables are going to heat up, but I want to show you how much the voltage drops when we shrink the size of just these cables. We're going to leave everything the same from here down, but I'm going to show you what happens when we put the wrong cable size, and then we're going to optimize this at the end, and we're going to do kind of a best case scenario. So I'm going to take you to a worst case scenario, and then we're going to look at a best case scenario with the correct cables. We're going to optimize this, and I'm going to show you the difference in voltage drop and how much power we're losing between the worst case and the best case. And at the end, we're going to wrap up with a few general tips for how to reduce voltage drop and increase the efficiency of your electrical system. But before we get into that, if you're interested in not just your charging and voltage drop, but your overall power system for your van or RV, I have a resource that you may be interested in called the Ultimate Van Power Cheat Sheet. It's got some great discussions on the different battery types that are available and the strengths and weaknesses of those. It's going to talk about the 3 major charging sources for vans and RVs, which are solar, shore, and alternator power. And it's going to discuss the strengths and weaknesses of each charging type and talk about how, brought together in a holistic power strategy, they're going to make sure you're covered no matter where you go out on the road. So if you're boondocking out in the desert or you're plugged in at a campground, you're going to be covered and you're not going to have to worry about your electrical system and potentially running out of power. There's also a really cool diagram that's going to show your entire system from top to bottom. It's going to show those 3 major charging sources at the top and how they link through the system, how they play nice together, come together to charge your batteries and then get distributed to your end devices. So that is also included in the Ultimate Van Power Cheat Sheet. That is a really cool diagram as well. To get your own copy, all you have to do is click that link below or go to rosslukeman.com/vanpower. All right, with that, let's go ahead and take some voltage readings. Step 1, we have to turn our system on. I'm going to plug in our charger. Now I've run down our battery so that the charger will go into bulk mode, and what that means is it's going to charge at a full 30 amps. Once the battery gets full, the current, the amperage is going to start to go down once it reaches its set point voltage, which is 14.4 volts in this scenario, or 14.2, excuse me. What I've done is I've run that battery down, so we're in the middle of the charge cycle. This thing's going to put out 30 amps consistently, and what I want to do is have that 30 amps running through the wires, so as we change these wires, we have a consistent baseline of 30 amps to measure from. So what we're going to do is we are going to take the voltage here and we are going to take the voltage here, and that is going to give us our voltage drop. So let's get the multimeter out. We're going to be taking a lot of measurements, so I will put my numbers down at the bottom of the screen. I'm not going to zoom in on the on the multimeter for each of these measurements, so you have to trust me a little bit here. So what you're going to do is take a voltage reading. We are at 13.75, 13.76 volts. Okay, we're going to come down to the battery. 13.56 volts. So that is a 0.2 volt. 13.76 minus 13.56 is a, what is that? 0.2 volt difference. So we're losing 0.2 volts. Not too bad, actually. Now that voltage drop is at 30 amps. So if we were to reduce this to 15 amps or 7 amps, that voltage drop would proportionally reduce as well. All right, stop the video. Cut. What are you doing? I'm in the middle of filming. You forgot to tell them that they can just raise the voltage of the system and it reduces the current. Problem solved. This video is about reducing voltage drop at a given voltage. I've got a 12 volt battery here. We're just going to talk about how to measure that voltage drop. Just tell them to increase the voltage to 48 volts. You're done. All right. I'll tell them a little bit about that. So as my uncle said, if you increase the voltage of the system, you're going to proportionally decrease the current to arrive at the same number of watts going through that line. And so what a lot of people want to do is just go from a 12 volt battery system up to maybe a 48 volt, and your current through those lines is going to be 25% of what it would have been with the 12 volt system. So if that's confusing, just think of as the voltage goes up, the current goes down in order to produce the same number of watts. We multiply volts times amps of current to arrive at the watts. Increase the voltage, reduce the current, and a lot of people walk away at that point and they say, problem solved. We've reduced the current, and so we've reduced the voltage losses in those lines because our current is a fraction of what it was before. However, in van or RV electrical systems, you have to look at the overall picture, and with a lot of 12 volt devices, we're now going from, say, a 48 volt system back down to 12. We have to have a converter in there, which may be 90 to 93% efficient. So we've now reintroduced a 7 to 10% loss that was not there before when we were running 12 volt devices off of 12 volt batteries. You just hook them up. There's no conversion there. So you don't have efficiency losses. So sometimes when you increase the voltage, we are solving the voltage loss problem, but we're now reintroducing other devices that have their own efficiency losses. So we're trading efficiency losses. And what I've seen with the 48 volt systems, I talked to a guy, he had trouble getting solar to go, because the way it works out with solar is if a 48 volt system is really going to be about 56 volts in the morning when you wake up. So your solar array has to climb to 56 volts and more realistically about 5 volts above that in order to start charging those batteries. And if you have a van or RV and you can get all your panels and hook them together in series and try to get that voltage as high as you can. But in that guy's case, he just gave up and said, yeah, I'm not doing solar. I'm going to have this big alternator and we're going to fast charge the batteries. So you have to look at the big picture as you increase the voltage of the system in a van or RV. In a house, fine. You're going to go from 48 volts and you're going to pretty much make inverter power at 120 volts, 230 volts, depending on where you are in the world. So yeah, I have a 48 volt battery system, but in vans or RVs, it's kind of a different story. So it's something to pay attention to. So what do you think? Don't be a pansy. You need more voltage. More voltage. All I'm saying is that when you bring the battery voltage higher in van or RV electrical systems, it has other implications than just reducing voltage drop. All right, he's not happy, but we're going to move ahead anyway and talk about reducing voltage drop. So we're going to hold it at 30 amps, and those are kind of our starting numbers. Now let's do something cool. I'm going to turn all this off. We're going to switch the wires from 6 gauge to 12 gauge. So these are too small for this charger. Don't try this at home, but we're going to put the 12 gauge wires. We're going to check that voltage drop, and we are going to see what happens. All right. All right, so we've got our 12 gauge wire set up. It is a 2-conductor marine cable, so there are a positive and negative running through there, as you can see as it exits there and hits the positive and negative bus bars. So what we're going to do is we're going to turn this on, and we are going to look inside the charger. So I have the phone set up with the Victron Connect app. We'll pull up the charger, and I'll show you a little bit of what has happened. And then we'll come back out and we'll take our voltage measurements and make a comparison. I'm going to turn the battery switch on. That is going to crank up pretty quickly. And let's go ahead and pull up Victron Connect. I'll zoom in here on my phone. All right, so we can see on the battery monitor here, this is a BMV 712 from Victron. You can see we've got 28.79 amps coming into the battery. So this is a 30 amp charger. A minute ago, I can tell you it was putting out right at 30 amps, but with the smaller wire, it's not able to put out the full 30 amps. So let's go into the charger itself, and I'm going to show you the voltage drop. So 28.8 amps, so that's about what the battery monitor was telling us. So because the wire is so small, it is trying to get 30 amps through there. It actually reduces the amperage that the charger is able to put out because of the resistance in that line. And the real revelation is here. So the output of the charger, it's calculating is 14.56 volts, only 13.6 at the battery. So all of that voltage in between there is being lost. All right, so let's take our own voltage readings and we can kind of make a comparison to what we saw in the app. And ideally, you would be able to take your own readings and not necessarily rely on the app. So I want to bring it real world and show you how these calculations are made. So let us measure at the charger. It's still putting out close to 30 amps, 14.66 volts. We can compare that to what we saw on the app. 13.63 volts, 64 volts. So 1.02 volts lost between here and here. Now, I know that Victron would not recommend using a 12 gauge wire here. It's getting a little bit warm. As it warms up, the resistance increases slightly as well, which is not good. The main thing we want to look out for is catching this insulation on fire. But that's kind of a worst case scenario. What I'm kind of trying to show you today is you may not want to use the absolute minimum wire size so it doesn't catch on fire. There are other considerations such as voltage drop where you're losing power. And I can tell you, if we do our calculations here, 1.02 volts, right, at 28.8 amps. So 1 times 28, if we take the voltage of 1, it was 1.02, but we'll call it 1, amperage of 28.8, volts times amps equals watts of power. So we are losing 28 watts. Based on those calculations, we're losing 28 watts between the charger and the actual battery. So all this inefficiency The charger's trying to put out about 400 watts. 28 watts are just being wasted to heat. So this might as well, we could use this as a heater coil for our water tank or something like that. It's putting out significant heat because our gauge is too small and our length is 9 feet and it doesn't need to be that long. So let's take those numbers. This is our worst case. So we lost 1.02 volts between here and here. Now I'm going to change the board and we're going to take a calculation in kind of a best case scenario, and then we'll wrap up with a few final tips. All right, so I've set up kind of a best case scenario here. We've shortened our cables a little bit, and let's go ahead and take a look at the voltage drop and see what we have from this scenario. Turn on our battery switch. And one of the reasons I turn off the battery switch is it makes all of this dead, and so as I work with this cable, there's no voltage going through there. But anything below that is live, so just be careful if you're setting something like this up. But our charger has cranked up and we are now charging the battery. Let's go ahead and take a voltage reading. We'll start out at the charger. We are looking at 13.70 volts. The battery, 13.5455. So it said 13.70, and then at the end it said 13.71, and then this one creeped up 13.55. So we're looking at 71 minus 55 is 16. So it's 0.16 volt is the drop between here and the battery. So if you recall, when we had it up here, it was 0.20 volt. So it improved, but just a little bit. But you can see the effect that the cable size had when we used the 12 gauge instead of the 6 gauge. We had unnecessary length, which sometimes in these vans and RVs, there's a reason to go a long distance. And I wanted you to see what happens when you need to go 10 or 12 feet. And that's the design of your space. You know, it happens sometimes. You have those batteries underneath, you have to put them in a certain spot, and you need to run 10 feet back to your power system. I just wanted to show you the type of voltage drop that occurs and the effect that a larger cable has to reduce that drop. And as we saw with the 28.8 amps multiplied by 1 volt, we're losing 28 watts of power between the charger and the battery with the worst case scenario. Let's see if we do this calculation. 0.16 volts of loss times 30 amps. We're back to a full 30 amps with this larger cable here. 4.8 watts. So we are losing 4.8 watts. Now this is putting out about 400 watts. So 4.8 is being lost. We'll call that 5. So it's putting out 400, only 395 watts are making it into the battery. So it's pretty good, but as you can see, that voltage drop is always there. And some of the other things that we can do to reduce the voltage drop, other than use sufficient cable size. So the cable thickness needs to be sufficient. Reduce that cable length if you can. Make sure all of your connections are tight. So you want to, if there are torque specifications for particular components, see if you can find that on the specs for that item and go ahead and torque it down to that torque. Now you don't want to overdo it because that can also cause problems. So just make sure that they're sufficiently tight. You want to have high quality components. So I've noticed with some of these bus bars, they are nickel plated brass. brass is not as good of a conductor as copper, but it's cheaper, right? So if you find that bus bar and you're like, oh, it's only $20, this looks great, or 2 for $20, be careful because you're causing, voltage drops through poor equipment. So copper is a little more expensive. I would not try to get the cheapest components you can absolutely find because you may be causing permanent voltage drop and you're going to have power losses between your charge sources and your battery. And if you think of something like solar, you're trying to maximize the amount of power off of those solar panels, and you need to make sure that that actually makes it to your battery. But if you have all sorts of speed bumps in there for those electrons to slam into, you're going to lose a lot of that power and it's not going to be as efficient. So you're not going to get as much battery charging per hour of sun as you could have with a system that was designed a little bit better. One other thing I wanted to show is on the switch here. This has the largest voltage drop. What you can do, we're used to measuring voltage between positive and negative like you saw here. But what you can do when it's under load, so we have 30 amps running through here, is you can measure positive to positive. So any point in the system, we can go from the positive output of the charger to where it hits the battery, and we can calculate a voltage drop there. So let's go ahead and do that. We are looking at 0.122 volts. Not too bad. Now we have to remember that also happens on the negative side. It may be a little bit different because we have a different setup over here. Get my prong in there. 0.026 volts. So we're actually losing more on the positive side than we are on the negative side. But remember, those electrons, they have to run the full race course. So they're running through the positive, they're running through the negative. So we're losing more on this side than this side, but the aggregate is measure the voltage at the charger, measure the voltage at the battery. That was the 0.16 volt. That's the total loss between the positive side and the negative side. And if we measure the switch, we're looking at about 0.1 volt or 100 millivolts. So a lot of the losses will be measured in millivolts, which is 1,000th of a volt. But the switch is the biggest culprit. I've measured it up to 120 millivolts. The bus bar between here and here, about 1 millivolt. 5 millivolts on the fuse. So that is my lesson on voltage drop. Hopefully that gave you some ideas. And we can run calculations and take the ohms of resistance in a cable and calculate it out. But I really wanted you to see the numbers that I saw when I was charging this battery the other day. And the effect on that cable size and the cable length, it can have a large profound effect. So hopefully that gives you some ideas on how to reduce voltage drop, which is waste, in your electrical systems. I hope that was useful. Again, if you want help with your overall electrical system, not just the voltage drop scenario, you got to grab a copy of the Ultimate VanPower Cheat Sheet. Just click that link below or go to rosslukeman.com/vanpower. Thanks for watching, and I'll see you in the next video.